Welcome to the GSIP online training program. Today's module is entitled Introduction to Design of Experiments module. The purpose of this module is to define possible DOE applications. Now, when I see DOE, that's an acronym for Design of Experiments, and people refer to it as DOE. So we're going to teach you how to design experiments. And it's one of the more powerful tools, really, in the Six Sigma or Quality Engineer's toolbox. Very, very powerful. And most people consider it to be the calculus, if you will, of Six Sigma or of quality engineering. That's not that hard. If you understand what we've done basically so far, the inference studies and correlation coefficients, etc., this is really going to be fairly simple, in my opinion. And so I wouldn't get too stressed out about it quite yet. I think you'll be fine. Okay, and also to understand how to model a process using design of experiment tools. By model, I mean mathematically modeling. To understand the DOE methods used to optimize processes. So that's what we're going to do. In fact, notice I have this little paper airplane with me here. We're going to use that as we go through this lecture to understand some of the principles. I think it'll make it easier. What is experimental design? Designing an experiment in such a manner that the information gathered is relevant to the problem being investigated. Okay. Using gathered information to optimize and model a process. And perhaps the most key element of all of these three bullet points is the last one. And ultimately, the objective of an experimental design is to provide the maximum amount of useful information at the minimal cost. Throughout periods of time we give them names. So there was the Stone Age, the Bronze Age, the Iron Age. And anyway, we come up to our day. It's called the Information Age. Well, if it's truly the Information Age, think of that. We're in the Information Age. Doesn't that make this quite a bit more important? Let's read it again. Ultimately, the objective of an experimental design is to provide the maximum amount of useful information at minimal cost. In other words, what you bring to the company when you understand DOE principles and all these other principles we've been teaching you is you can bring them information at a I'd say at a wholesale price. That's what makes you worth money to your employer. And we can most certainly teach you how to do that because this is the tool that can get it done. Very powerful. Why use experimental design? Well, you can use it for a lot of things, and these are all probably a subcategory of process improvement. I could just leave it at that. So I threw in a bunch of categories of process improvement. Process optimization, where do you turn all these gauges to get the optimal output? We can do that mathematically with DOE. Process improvement, reduce process variability. Remember solution 3? I use DOE for solution 3. Remember solution 3 is reducing variability. So that's a very powerful thought there. Creating robust processes. A robust process means that you create a process and when the temperature changes or the humidity changes or you get a different operator in, the process doesn't care. It keeps giving you the same output even when the environmental factors change. And if it can give you the same output even when things change, that's called a robust process. And if you're in manufacturing, you realize manufacturing can be a pretty tough way to earn a living at times. I remember being a plant manager over a manufacturing facility, and I went to pay my insurance bill, and I went into the insurance office, and they're playing elevator music and probably making double the salary I was. I thought just doesn't seem fair. But we could do that. If we were good at creating robust processes, your life would be a lot easier in the world of managing processes, trust me. But we're not. We're not good at it. We don't even usually consider it in our day-to-day thought. How can I make this process robust? But if you can, you could be at your desk playing elevator music while everything's running just great. Okay, but because we don't create robust processes, then we create our own environment of stress and frustration. And the guy who's known for this, the guru of creating robust processes, is a guy by the name of Taguchi. So when you hear of robust process, you should think of Mr. Taguchi. Confirmation of process settings. Do we have everything set up properly? Well, that's kind of right up here with process optimization. So there is some repeats on this one. I apologize. Product development. You could sure use it in product development. People should, and a lot of books are written about it, but not many people do it, to be honest with you, at the time of this recording anyway. Process development, product development, same. So you can also do it on processes. Design development, kind of repeat of product development there, but anyway, gives you an idea. You can use DOE for improving things, in short. I always tell people you can either read a book or you can run an experiment. But if you run an experiment, you'll probably know more than the person that wrote the book. In fact, I ran an experiment once and I ended up writing a book about it. And I came up with stuff that no one else understood about this particular process. Okay, a lot of this module is about definitions, vocabulary, and that's what this slide is on, vocabulary. Response variable, that's your why, so it's all about mathematical modeling. A lot of this DOE stuff is mathematically processor phenomena mathematically. And the response variable is the why variable. It's the dependent variable. But in design of experiments, we call it the response variable. So now I'll bring out my airplane. And the response variable is what I'm trying to optimize. And so in our little make-believe experiment here, I'm going to try to optimize flight distance of this airplane, flight distance. So my response variable is going to be flight distance. Parameter or factor. Its factors are variables that you feel are going to have an impact on the response variable. Well, what are those called? Those are called independent variables, per our discussion on linear regression. So there's our dependent variable y, our x variable, independent variable. And for our little experiment, I'm going to pick two variables. One is going to be nose condition, and nose condition means I'm either going to have this folded out. That may be hard to see, but I fold it in the nose because I think it may fly further when I fold in the nose. And so, or I could have it out. I don't think it'll fly as far, but I don't know. I haven't experimented with it, but now it's folded out. So my variable nose condition is one of my variables. My other one is wing condition. So nose condition and wing condition. And wing condition, I think if I fold these up, it's going to give me some stability in this little airplane, and I think it may fly further. So I'm going to experiment with that. But that's my two variables. Nose condition, wing condition. Now, level settings. I kind of went through those already, but I didn't define them as such. So let's look at this one first. My nose condition. The nose condition on the airplane. That's the factor. There's two levels on this factor. One, the nose folded in, which I think it will fly further. That's the hypothesis. And the other level or setting is the nose is folded out. See how pointed it is now. And so one factor, nose condition. Two level settings, folded in, folded out. I think it's going to fly further when it's folded out, to be honest with you. So we're going to call this, when it's folded in, the positive setting, and when it's folded out, it will be the negative setting. So let's review here. Response variable, flight distance, it's what you're trying to improve. Parameter factor, nose condition, wing condition. Level settings, level setting for the nose is folded in, is positive, folded out is negative. For the wing setting, I think it'll fly further when I fold the wing tips up, so I'm going to call that positive. I'm going to call this negative when the wing tips are folded down. So that's what we have so far. Response, factors, level settings. Factor effects. What's a factor effect? Well, let's say I throw this airplane and it goes, who knows, 20 feet. It goes 20 feet. And I say, okay, 20 feet. And then I fold this in and I throw it when the nose is folded and it goes 25. Then the effect is 5. because when I folded it out, it went 20. When I folded it in, it went 25. So I'm assuming that that nose condition increased my response by 5 units. Okay? So that would be called the factor effects. And that's exactly how you calculate effects, by the way. You throw it this way, then you throw it this way, and see how much further it goes, and that's your positive, or that's your called your effect. It's pretty easy. However, I may do it multiple times. In fact, I am going to do it multiple times. And what you're going to do is you're going to take the average when the nose is folded out, the average, then I'm going to take the average when it's folded in, then I'm going to subtract the average, I'm going to take the flight distance when it's folded in, I'm going to subtract the flight distance when it's folded out. The average flight distance, the average. So I'm going to be taking the averages when it was in, averages when it's out, subtract the two, and that's the effect. What does the effect mean? It's on average the difference in flight distance at the different levels, folded in and folded out. That's called a factor effect. Then of course I'll do the same thing with my wing condition. I'll throw it maybe 5 times with these folded up, write down the average, and then I'm going to fold these down, throw it 5 times, write down the average, subtract it. That will be my effect. And that's really one of the more difficult elements of DOE is calculating effects. Well, how difficult is that? That's pretty easy. Don't make it more difficult than it is. Because most students do. They get in their mind, oh, this is the calculus of 6 sigma. This has to be, no, it doesn't have to be hard. It's subtracting 2 numbers to get the effect. Come on. It's not that hard. Students tend to make it more difficult than it really is. So be careful. That's how you calculate effects. And we're going to calculate some effects even in this introduction module. But guess what? I already told you how to do it. That's what we're going to do. Take the average when it's positive and the average when it's negative, subtract the 2. You get the effect. Okay, then there's noise. Noise, I think there's 3 types of noise. There's environmental noise. What if I was throwing my airplane and the air conditioner came on and pushes it into the ground? Oh, that's a variable that had an impact on my response variable, but it wasn't one of my defined factors. Okay, we call that noise. It's environmental noise. Then there's unit-to-unit noise. What if I had more than one airplane that I had to build for this experiment? Well, if you've played around with paper airplanes, you know every one is, even though you try to make them exactly the same, one goes to the left, one goes to the right, one goes up and down, and there's just some difference there. And so that's as noise also. It has an impact, but you can't control it. It's called noise. Okay, and then there's wear. When I'm experimenting with this, eventually it's flying pretty good, but man, I hit the nose enough time, it dents up the nose, kind of crumples up the wings a little bit, and it changes the flight characteristic. So that's noise, just wear over the range of the experiment on what you're experimenting with, such as a paper airplane. So noise is a problem. Now, one of the powerful elements of DOE, if you work it right, and I'm not going to show you how to do it right now, but if you work it right, you can screen out noise. That's pretty powerful. Okay? Robust design. We talked about robustness a little bit ago. Remember, if the environment changes, the process still works the same. I was teaching a DOE class at an aircraft manufacturing facility, and I gave them a contest, and I threw up some money and said whoever does their DOE, comes up with the best design, will win so much money. So they were all excited. Unfortunately, the day of the competition came. They took us out in the hangar and they opened up both doors. They were doing some work. So they'd throw the airplane, it'd flow backwards. So we're getting negative results. It was terrible. But one group come up and I made a rule. I said you can use paper clips. Well, rookie mistake on my part. I didn't tell them how big of a paper clip. So these one guys came to class with this huge paper clip and clamped it onto the airplane. The paper clip was bigger than the airplane. And they threw that thing and it flew like a rock, which was better than anything else flew that day. And it didn't matter that those doors were open. It would fly the same either way. That's called robustness. Robustness. Even when the wind came in, didn't make that big of a difference on flight. That's called, again, robustness. Orthogonal design, we'll talk about that later. Full factorial design, is when I run an experiment and I run every possible factor level condition. I run every possible combination of factor and level setting. There is nothing left. I run every possible combination. That's called a full factorial design. Replication, if I just throw this once, okay, nose folded in, it goes 25. Nose folded out, goes 20. Okay, the effect is 5. That's if I just do one. That was one replication. You can do that. But you're better off doing multiple replications. So I do 5 folded in and 5 folded out. Now that's a replication of 5. So that's much better. You're going to find that replication is extremely important in design of experiments. Sum of squares, we've already talked about that before. Remember when we did sum of squares in the ANOVA study? It was x bar minus the x's and squared, and then you add them all together. So you've heard of that. Factor effects plot. We'll go over that formally later. Factor interactions. Okay, that's an interesting thought. What if I threw my airplane that went 20 units with everything flat here? The wing conditions flat, the nose conditions folded out, goes 20 units. Okay, then I fold in the nose and I throw it and it still goes 20 units. So I say, okay, then I fold my nose back out and I fold the wing tips up, still goes 20. In other words, the effect of all those variables is 0. But then let's say I fold the nose in and I fold the wing tips up. Now it goes 50 units. Whoa, that's more than double. What's going on here? Well, there's an interaction between these two variables. In this case, it really had a positive impact on flight distance. Those are called interactions. However, just for the record, remember, you could throw this, it goes 20, and I fold the nose in, it goes 25, and the wing tips may have an effect also. They can have an effect and you can still have interactions. The example I just gave, the main effects had 0 effect, but when I combined the wing condition and nose condition folded up and in, it went a lot further. So that would be an interaction. Okay, so there you have it. Hopefully that makes sense. And then a fractional factorial design is when you have a full factorial design where you run every possible combination, nose folded in, wings folded up, nose folded in, wings not folded up, etc. Every possible combination, and you take some of those runs out. You say, I can't afford to do all those things. It's too expensive. So I'm going to take this run out and this run. You start throwing runs out. And when you're finished, you have what we call a fractional factorial design. So if the full factorial design on this one, 2 variable, 2 levels, I can tell you right now it's going to be 4 runs for the full factorial because I know the mathematical equation. I'll teach it to you later. So that's a full factorial. But I say, no, I can't afford to throw this 4 times. I can only throw it twice. Oh, twice? Okay, that's a half fractional factorial because I'm only using half the runs, half fractional factorial. Then there's quarter fractional factorials, etc. But that's what a fractional factorial design is. You do not run all possible combinations of factor and level settings. Okay, so I've covered a lot of this already. Let's go over it formally and review it real quick. Response. A response is the process or system's measurable output. It's what you're trying to improve, in this case, flight distance. Factor. Factors consist of variables or parameters that are expected to have a significant impact on a process or system's output variable. Nose condition, wing condition. Got it. Factors have an impact or effect on response variables in 2 ways. This is important to remember. It can impact the average flight distance, and it can also impact the variability. So you need to take into account both of those in most design of experimental applications, or at least I'd recommend it. All right, illustration of factors and responses in a process. We've already talked about factors and responses, so I'm not going to read through that again. Level. Levels are predetermined settings for the experimental factors. For relatively high settings, a plus sign is used. So on my nose condition, since I think it's going to fly further when the nose is folded in, there's a blunt edge there, folded in, I'm going to call that my plus setting. And if I fold it out, I will call it my negative setting because I don't think it's going to go as far. I could be wrong, but that's my first thoughts. So for relatively high settings, a plus sign is used. For relatively low settings, a negative sign is used. Now, if you picked this being positive, nose folded out, in the end, the math will work out. But I like to have some logic behind why I do things. So if I think it's going to increase my output variable in the direction I want, I call it the plus. If I think it's going to hurt it, I call it a negative. And later on in the experiment, I'll find out if I'm correct or not. Okay. So here's an example of factor level settings. Let's say I'm experimenting with temperature. I think temperature may impact flight distance. So I do negative is going to be called 65 degrees, and positive will be called 95 degrees. And humidity, negative, I'll say low humidity, and positive is high humidity. Now, I have to define what low and high is. See, this is attribute data here, low and high, but that's important to remember. You can use attribute data in DOEs, and it often is low, high, for example. Now, you may have to define low as from 0 to 20% humidity, and then define high as 50% and above, or something like that, and you experiment with the high and low value. Okay, pressure, negative level, 12 psi, positive level, 18 psi. So notice on this one I just went numerical. The lower number is my negative, my higher number is my positive. So you can use that logic in some cases also. Okay, and obviously this is some different experiment, but now let's do the airplane one and experiment with this for a while. Notice run number 1 here, and that's what I'm defining right here. Run is a combination of level settings for each factor in an experiment. Okay, so let's look at run number 1. Nose condition, keep it folded out. Okay, I have it folded out. Got that, check. Wing condition, out. Okay, got it. Now I throw it. Record it. It's 120 inches. I come back here and write this in. Now I may test it 5 more times. You can do that. 5 times, 5 replicates, and I have 120, 118, 122, 125, 117, whatever. And I get 5, and I can take the average of those flight distances if I want to do replicates. In most cases, you want to do replicates. Since I want to keep this simple, I just kept it one value. Now, run number 2, it says, okay, run number 2, John, nose condition, fold it in, that's my positive. Now, I put out and in by your plus and minuses. I'm being nice. Usually in DOE, they just go minus, plus, and down here they say, on nose condition, minus means fold it out, positive means fold it in. Makes it easier to document that way. So I'm being extra nice to you today. But run number 2, fold the nose in, and keep the wing condition the same as run number 1, keep it out. Okay, and I say, okay, got it. The experimenter says, okay, do your throw. And so you throw it, and it goes 147 units. There it is. And you say, okay, very good. Let's write that down. Let's go to run number 3 now. And run number 3 says nose condition out. Okay, I have to change that then because last time it was in. So I fold it out. Notice it has a point on it now. And my wing condition needs to be up. Okay, so nose out. Wingtips up. Okay, got it. You can see my wingtips are up, and you can also see the nose is out. I throw it. There it goes. I go measure it. 150. Okay, write down 150 units there. Got it. Okay, let's move on to run number 4. Let's look at run number 4. Nose condition. Okay, fold it in for run number 4. And wing condition, you keep it the same as the last one. And that is the wingtips up. Now I'm ready to run my 4th run. I throw it, and I measure it. It's 166 inches. That's how you run the experiment. Okay? That's how you run the experiment. And there'll always be this same pattern, by the way. Notice my first variable, minus, plus, minus, plus. Then the next column over, you always double the number of minuses. minus, minus, and whatever you start out with, you run the same pattern on positive. I had one negative, one positive, one negative, one positive. The next column would be two negatives, two positives. If I had another column and 8 runs, which would be if I had another column, I'd have four negatives, because this had 2. I double the number of negatives each time. 4 negatives, 4 positives. Next one, if you had another column, it would be 8 negatives, 8 positives, 16 negatives, 16 positives. Okay, and that's how you set those patterns up. This is a full factorial design, by the way. Now, how do I calculate the effects? How do I calculate the effects of nose condition? That's an interesting question. Well, this is what you do. You take the average when it was in its negative setting. There's the negative setting, was run number 1, and it was 120. So take 120 and 150 and take the average of those. What am I doing? I'm calculating the average when nose condition was negative. Then I take the average when nose condition was positive, which was 147 and 166. So what I'm going to do is I'm going to move over to the whiteboard right now, and we're going to check this out, and I'm going to show you how to calculate effects. I've already explained it verbally, but I'm going to actually do it with you is what I'm going to do. And here's the matrix, and I think I may be able to give you a better shot. At least I'm going to try, so you can see that better. Yeah, that'll be better. So here's our new shot. Okay, so here's the experiment. I've written everything down, a little sloppy perhaps, but there's the nose condition, wing condition, and flight distance. Okay, notice I've made the negatives red and the positives black so that I can identify those. And I'm going to calculate, the first thing I'm going to do is calculate the effect of the nose condition. Well, I'm going to calculate the average when it was at its positive setting. In other words, the average when the nose is folded in. And the average was 147 and 166. So notice I come over here, I put a little sign there so I know this is my average calculation for when it was positive, and that's 147 and 166. Okay, positive nose condition, positive nose condition. And of course I'm adding those together, divide it by 2, and that's the average flight distance when the nose is folded in. Okay, on average then, when the nose is folded in, it went 156.5, whatever units, inches or whatever. Okay, so I found the average. Now I need to find the average when the nose condition was at its negative setting, which was what? Folded out. Okay, let's look at that. Folded out, negative, it went 120 and 150. So there it is, 120 plus 150 divided by 2 equals 135. So this was my average flight distance when my nose setting was in positive, folded in, and this is when it was negative, folded out. So by all appearances, it does appear that I was correct, that when it's folded in, it will go further. And now we need to subtract those two averages to see what the average effect is. The average effect of nose condition is 156.5, average when it was folded in, and minus average when it was folded out, gives me 21.5. That's the effect. That's the effect that nose condition has on flight distance. What did we do? We just subtracted a couple averages, so it's not that hard. Now let's do it for wing condition. That's an interesting one. We've already done it once. Now let's do it for wing condition. I'll get my eraser out here, and I'm going to now do wing condition. I'm going to start out doing it for the positive, so pay attention here. Okay, so I'm going to do positive first. So this is wing condition column right here. I'm on the right column. That's when it was positive. It went 150 and 166. So I'm going to go 150 plus 166 divided by 2 will give me my average there. That's kind of a weak pen, isn't it? I think my red is actually better. So I'm going to color that in so you can see it. 150 plus 166 divided by 2. That's a 2. Now I'm going to get my calculator out, and I'm going to go 150. I can throw that up there if you want to see it. 150 plus 166 equals divided by 2. So it's 158. Okay, so let me write that down. 158 equals 158. That's my average when my wing condition was positive. In other words, the wing tips were folded up. Okay, now let's do the negative, and the negative is going to be wing condition when it was negative, or these two here, 120 and 147. So I'm going to go 120 plus 147 divided by 2. So let's clear that out. 120 plus 147 divided by 2 equals 13.35. Oh, 133.5. Yeah, that makes sense. 133.5. Okay. And there we have it. Let me move out of the way so you can see that. It cut off the 0.5 there. But this was my positive for when the wing tips were up. This was the average flight distance. This was my average flight distance when the wing tips were folded out. The negative setting is what we'd call it. And there I have my two averages. Now I'm going to calculate my effect. How am I going to do that? I'm just going to subtract those two averages is all I'm going to do. So let's go and do that. By the way, we're going to use these later, so you should be writing these down. Remember, the nose condition effect was 21.5. I have it written down. You can't see it, but I am recording those. Now let's subtract these two averages to get the effect of wing condition. So 158 minus 133.5. Now, if it's a negative effect, you need to record it as such. You always need to take the positive and subtract the negative average from the positive average. If you need to be consistent or you're going to get in trouble. So notice I did my positive first, 158, and then I subtracted my average from my negative setting. So I take my average of my negatives and I subtract it from the average of the positives. And I do that every time. Consistency is very important. If it's a negative effect, you need to record it as such. What does that mean? In my case, it would mean I guessed that it would have a positive effect, and it did not. I was wrong. Of course, this way I'm going to be right on both of them because I'm going to have positive effects. So 158 minus 133.5 gives me an effect of 24.5. So I'm going to write that down. Effect equals 24.5. So the nose condition had an effect of 21.5, wing condition 24.5. So it appears that the wing condition had a larger impact on flight distance than did the nose condition, which kind of surprised me a little bit. Okay, but that's why we run experiments, is to understand the effects. All right. I'm going to erase this. I recorded my nose condition effect already on both the wing and the nose effects. They're both recorded. 21.5 for nose, 25.4 for wing, assuming I did the math right. Hopefully I did. And hopefully you're following along with me, and if I got it wrong, you keep your correct numbers anyway. Okay. All right, now what I need to do is determine if there's an interaction between the nose condition and wing condition. Now this is going to be a little different, and so I need to create another column for the interaction. I want to know if there's an interaction between the variables. And if there is, because maybe it has a bigger effect if I fold in the nose and the wings up together. That gives me an interaction It makes it go even further. I need to know that. That's important to understand. Very important. It's what makes DOE so powerful, is it looks at interactions. The linear regression we taught you, it didn't take into account interactions. DOE does, which makes DOE powerful in many respects, more powerful than your traditional linear regression, because we do interactions. Okay, with that being said, we're going to create another column over here, and we're going to call that column the interaction column. I'm going to extend these lines to the table out. Okay, so everyone should be good with that. Since I'm not using this down here, I'm going to get rid of this part of the table. Now, how do we create the plus and minus signs for the interaction? We need some plus minus signs, so we need to know, take the average of the positives, average of the negatives, subtract, and get my effect. You can't do effect if you don't have plus minus definitions. Well, how do I get the signs for that? Well, I multiply them by the two. So if I want to know the interaction between nose condition and wing condition, I go minus times a minus is a positive. So I'm going to write down positive here. Oh yeah, that's a better pen. And positive times a negative, positive 1 times a negative 1 will give me what? A negative 1. Of course, we don't write down the 1. We're just doing this positive, negative. And what's a negative times a positive? It's a negative. Very good. Now, positive times a positive is a positive. And if it's an orthogonal design or a full factorial experiment, you'll always get half positives, half negatives. So if you don't, you did something wrong, okay? And go fix it before you go any further. Now that I've identified plus and minus signs for my interaction, now I can go ahead and calculate my effects the way I always do. So let's do the positive, average of the positives. There's positive 120 and the other one is 166. So I'm going to take positive for my interaction. I'll put it in parentheses there. And I'm going to go 120 plus 166 divided by 2. Let me get my calculator in hopes that I don't make a mistake. 120 plus 166 is 286 divided by 2 is 143. So 143 on average for my interaction there is when it's positive is 143. Now let's take the average when it's negative, and it's going to be 147 and 150. So let's do that real quick. And I think I'm going to have to put that up here because I'm running out of room, and that's okay. And I'm going to go 147 and 150. 147 plus 150 divided by 2. Let's go back to my calculator. 120 plus 166. Oh no, I knew I was doing something wrong there. Here it is, I'm working on this one. 147 plus 150 equals 297 divided by 2 gives me 148.5. And I'm running out of room, so I'm going to write it down here, equals 148.5. So again, the average when it was positive, the average when it was negative. Okay, so remember this is the negative. We always go positive first, then negative. So what's this going to give us? A negative effect. Okay, so 143, I'm going to write down here effect. EFF, since I'm low on room, is going to be 143, that's my positive, minus 148.5. Okay, and subtract those two. Now pull out my calculator just to make sure I don't make a mistake. 143 minus 148.5 equals minus 5.5 equals, yeah, there may be enough room there. You may not be able to see this one. Get out of the way, see if, yeah, it does. It just barely made it in. Oh, I forgot my negative sign. So remember that's negative. So the effect of the interaction is minus 5.5. So it didn't have as big of an impact as my main factors, which, you know, is fairly common, but sometimes you get surprised. And when it surprises you, it means no one figured that out logically, and it can become a huge competitive advantage for your organization if you understand interactions. Okay, so now you should feel comfortable calculating effects. So what results is what? Well, our wing condition was the highest effect. It had on average 25.4. It went on average, it went 25.4 units further when the wing tips were folded up. Okay. The second most important factor was nose condition. On average, when I folded the nose in instead of out, it went 21.5 units further. I have those written down. That's why I keep looking over there, make sure I get it right. And the interaction, when it's negative, it's negative 5.5, the effect of interaction. So it's actually hurting us. And so that's how you do it. Now, what I'm going to do next is I'm going to create the mathematical equation for this. So let me erase the board so I have a fresh start here. And let me write down all the results of the experiment. Wing condition, I'm grading it from greatest to least. Wing condition had an effect 25.4. Nose condition was second place at 21.5 effect. And the interaction equals negative 5.5. Okay. Now I need one other thing that I didn't get, so I'm going to switch from the whiteboard real quick and go back to the PowerPoint. Since I erased my matrix, I'm going to have to pull it back up here because it's important that we do one other calculation. And the other calculation that we're going to do is going to be the average of all of these responses. And we'll call it the grand average. So let's plug that into the calculator and see what that is. So I'm going to take the average of 120, 147, 150, and 166. Okay. And it gives me an average, so I'm going to write that down. Average responses. I'm going to call that X bar, if you don't mind. And the average response was 145.75. Okay. Now I have everything I need, so now I'm going to go back to the whiteboard. And we'll play around with some more math. Remember, what I'm doing now is I'm going to create a mathematical model that will describe to you how far you'd expect an airplane to go based on the setup of the airplane. So I'm going to call the flight distance FD. I could have called it Y equals, but I'm going to call it FD. Flight distance equals, and this is my Y-intercept right here. 145.75 is my Y-intercept. So I'm going to write down flight distance equals 145.75. I'm not going to multiply it by any x because that's my Y-intercept. Plus half my wing condition effect, half of it. So let's pull it out, my calculator, make sure I don't make a mistake here. 25.4 divided by 2 equals 12.7. So the first coefficient for the wing condition is going to be 12.7 times the wing condition is what we're working on. So notice now I'm multiplying it by the independent variable setting. So you know this is the coefficient. When you see me multiplying by something there, you know I'm talking about a coefficient. So this is my first coefficient. Now let's do the coefficient for nose condition, which is going to be half of this 21.5 here, half of that. So 21.5 divided by 2 is 10.75. So it's going to be plus because it's a positive effect. So it's going to be positive 10.75 times nose condition. Now I'm running out of room here, as you can see, so I'm going to have to go to another line below this so we can see it. And the next one is going to be a negative because it's my interaction coefficient. So it's going to be a negative and half of 5.5, which is 2.75. So negative 2.75 times wing condition times nose condition. And then you could put plus error there for the variability about the linear regression line. We could add that to it as well. So that's the mathematical equation. Let me get out of the way so you can see the whole thing without me moving it out of the way. So flight distance is going to equal 145.75 plus 12.7 times the wing condition plus 10.75 times the nose condition minus 2.75 times the wing condition times the nose condition. Now, I'm going to test this equation, and I want to test it at positive and positive. Okay? So what I'm going to do, I want the wing condition to be positive, so I'm going to make that a positive 1. That's what the positive meant. I just didn't write it in there before, but it's a 1, so I'm going to go positive 1 in here. And I'm going to test the wing condition also at a, well, let's change that. Let's put a negative number in there and make it a little more interesting. Negative 1. So I want to test that at negative 1, so I'm going to put a negative 1 in there for nose condition. In other words, I want to know the flight distance when the wing is folded up and the nose is folded out. That's the negative. That's what negative means on that. Now, since I've already chosen those, I have to do the same here. Remember, this is wing condition, so I have to make that a positive 1, and this is a negative, so I'm going to have nose condition negative 1. So I'm going to change those. Positive 1, negative 1. All right. Now let's rewrite it. Of course, 1 times something is that number, so I can just take that out of there. And 10.75 times a negative 1 is going to make this negative. So I'm going to put a negative. You're going to subtract that. And a positive times a negative is a negative. And this is already a negative, so it's going to change it to a positive. Okay. Now let's run the math through my calculator. And it's going to be 145.75 plus 12.7 take away 10.75 equals plus 2.75. So my mathematical equation says if I do the wing condition positive and the nose condition negative, I get a 150.45. So remember that. Negative, positive on the wing condition and negative on the nose condition. So let's go back and look at that. And I can already tell you I made a mistake somewhere. All right, so I wanted to know when wing condition was positive, and nose condition was negative, was this run right here, 150. And I got 150.45, which means I did something wrong on my equation. And I'm not sure what I did wrong. I'd have to go back and look at it. And I think it may be my wing condition effect was off a little bit. But that's how you know if you did something wrong. If I did everything right, it would have equaled 150. And you probably, if you followed along, you probably already figured out what I did wrong. But the important thing here, I'm not going to redo it and find that mistake. I could do that on my own time. But the important thing I want you to know is how we did that process of coming up with that mathematical equation. And I want you to feel comfortable enough doing that. It's very important to do that. I'm going to give you another shot here of, there we go. Okay. So like I said, hopefully you understand the technique. Let's review. How did I calculate the effective nose condition? Well, I took the average when it was negative, 120 and 150, took the average of those two numbers. Then I took the average when it was positive, the average when it was 147 and 166. Once I got those two averages, I took the average when it was negative and subtracted it from the average when it was positive, and that's my effect of the nose condition. I did the same thing for wing condition. I did the same thing for the interaction. Once I had all those, I took the average of the flight distance. That was my y-intercept. Then I took my y-intercept and I took half my effect of the nose condition for my coefficient and half of the wing condition effect for the coefficient for wing condition, and of course half of the interaction for my interaction coefficient. Then I set up my mathematical equation. And on mine, unfortunately, I did something wrong there. But you understand the process. That's what's important here. Now, that was an introduction. We're going to do this again in the next module. We're going to do it formally, slide by slide. But I wanted to introduce you to the concept first. And if you can do that, you can do all DOEs. That's how you analyze them. That's how you create the mathematical equation. Okay, let's move on. Factor effects is an effect of a factor on the output variable is the change in the output variable when the factor goes from its low level to its high level setting. We knew that. Nose folded in, nose folded out type thing. And what they usually do, people like to see graphics. They relate more to graphs than they do just numbers. So you say, okay, when this was at its negative setting, it went 70 units. And when it was at positive, it went 77. So what's the effect? 7 is the effect. But they'll plot it out like this and draw a line, and the steeper the line, the bigger the effect. And so you may have many variables, but you can look at this real quick and see which one has the steepest line and say, oh, that has the biggest effect. And people like to look at graphs. There I'm calculating my factor effect. Response when it was positive. Response when it was positive, it went 77. When it was negative, it went 70. I subtract those two, get 7 for my effect. Hopefully you're comfortable with that. And I guess you could draw a triangle, and this side of the triangle would be the effect, if you wanted to look at it that way. All right, noise factors, a factor which is uncontrollable that has an effect in on the response variable. There are 3 types of noise. External noise, we've covered this before, by the way, this is a review. External noise includes environmental conditions such as humidity and temperature. So we can't control it because the heater comes on. We still run our experiment anyway. That's noise. Has an impact, but you can't control it. Unit-to-unit noise, that's where I made many airplanes, and they all had their different flight characteristics. So that would create another element of noise. Internal noise includes conditions such as wear and vibration. So remember, if I'm throwing the airplane over and over, I have a lot of replicates, it starts denting the airplane up, beating it up, and it starts giving you different numbers over the time of the experiment. That's called internal noise. So noise is an enemy to the experimenter. Now, this is how you screen out noise, and this is very important, so listen up here. The way you screen out noise is you have to run replicates. And you have to run them in random order. Let me explain. So let's say I'm going to run number 1 5 times. Well, if I run it 5 times, but right when I run my negatives, everything's good, and then I get ready for my positives, and the air conditioner comes on, and I throw it, and it buries it into the ground. So I ran replicates, but I didn't run them in random order, and as a result, the air conditioner only impacted it at its positive setting. That's not good. That'll mess up your experiment. You have to be very careful because experiments can be very expensive to run. I've run experiments that cost probably a couple $100,000 So you want to make sure you do things right. Now, let's say that you didn't run 5, so you had 10 replicates, 5 positives, 5 negatives, or let's say you do 5 negatives first, then 5 positives, but the air conditioner comes on with the positive, and it, on average, cuts back on the flight distance by 5. Okay? Well, let's look at this. Let's calculate an effect and see what happens when I run multiple runs in random order. By random order, what I mean to say is that I don't just run 5 with my wingtips up, 5 with my wingtips down. No, I run 1. Run number 1 was, let me go back, can't remember. Run number 1 was negative, negative. So my wingtips are out and my nose is out. So I'll throw that and I write down my, let's say it went 120, which is what it says there. And then next time I say, okay, what's next? They're in random order. Oh, the next one you run positive and positive. Okay, so I change it to positive and positive. Then you may run the number 2 run, plus and minus. And then you come back and say, okay, now it's time for my second run on negative, negative. Okay, negative, negative, got it set up, and you throw it, and this time, but notice I didn't do one right after the other. That's called running them in random order. Yes, I had replicates of 5, but I didn't run all 5 at the same time. I staggered them and I mixed them all up, random run order. Now let's go back to the whiteboard. And let's just make an example here. And let's say I threw at my positive setting, and I can't remember the numbers now, so I'm making them up. But let's say at my positive setting, it went 150 units on average. Okay, and I'm calculating my effect, so I'm going to subtract. And when it went on the negative setting, it went 140. We'll keep the math really simple. So what's the effect? I drew those kind of big, didn't I? But 150 minus 140, my effect is 10. Effect equals 10. Now, let's say on average, and I put these terms in the wrong position. I should have put them over here. Let's say on average, when the air conditioner comes on, I throw my airplane on average. It goes 5 units shorter. Oh, 5 units shorter? So it takes 5 off of this. But since I ran them in random order, it also has the same impact on my negative setting. So it also impacted that 5 units. So I have to subtract 5 because the air conditioning. Now, what would that give me then? That would give me, since the air conditioner came on, I would have got 150 without it, but I got 145. And I would have gotten 140, but since the air conditioner came on, it ended up being 135. Well, what's my effect? Oh, still 10. That's right. So by using replicate runs and doing them in random order, I screened out the noise, and the effects were the same, and the mathematical equation will be the same. It's a very important concept in DOE, screening out noise. And that's the preferred method. Run replicates and random runs so you can screen out noise. Remember, these are very expensive, so you don't want to take a lot of risk. And that's how you do it. And if you said, John, you have a choice here. You can either run fewer variables, because we only have so much money. You can run fewer variables and more replicates, or you can run more variables and fewer replicates. I'd say, and everyone I know that does this as a profession will say, I will take fewer variables and more replicates, because it allows you to screen out noise, and it'll help you on your inference studies that I'll teach you about later. So replication in random order, very important. Now, sometimes you can't do random order, and so they go into blocks, which I'm not going to discuss at this time, but we can discuss that at a later time. So, what did we learn here? Something very important. How do you screen noise out of an experiment? You run replicates. In other words, run one. You don't just run it once. 5 times is pretty good. 5 replicates. Okay, that's part of it. You ran replicates, but you have to run it in random order, so the phenomena, the noise, has the probability of affecting both the negative setting and positive setting equally. And if you can do that, you'll screen out all that noise. And that's very important. A very, very powerful concept in DOE. All right. So we've already covered that. Those are the noise. Remember, we can screen out noise. Robust design, a process whose output variable or response variable is unaffected by uncontrollable external, internal, or unit-to-unit noise. And that's where, man, these were flying pretty good till they opened up the doors and they made it a wind tunnel. Now it's flying back. But someone made it robust because they put a big old paper clip on there, just throw it like a rock. And it made the process robust. Even though the environment changed, it's okay. The process still gave me the same results. That's called robustness. And DOE can help us create robust designs. Orthogonal design, an experimental design that ensures the effects of any process parameter can be measured independently without the effects of any other process parameter. That's not going to make a lot of sense right now, but what makes it unique, you'll always have equal number of positive and negative values. That's one thing orthogonal will be. And it's also what we call a full factorial design. Allows for that independence. What is a full factorial design? An experiment that tests all possible combinations of factor or variable settings. Okay, all possibilities. I'm testing every possibility on this thing. That's a full factorial. As soon as you don't test every possible combination of factor and level setting, it's no longer full factorial. It's called a fractional factorial. And if you throw out huge amounts of runs, they call it a screening design. Screening design, man, you threw out 90% of the runs. Or something like that. A huge amount of runs you threw away. That's called screening. If you only throw out half of them, that's quite a bit, but that's called a fractional factorial design. If you threw out half the runs, it's called a half fractional factorial. Okay, enough said on that one. Now, calculating the number of runs for a full factorial design. How do we do that? Well, it's pretty easy. The base number is the number of levels. How many levels did I have on every variable? Remember, one of my variables was wing condition. Let's look at that. Wing condition, and it had the wings folded out and the wings folded up. How many levels did I have? 2. 2 levels for every variable. Because same way with my nose condition. 1 level folded in, 1 level folded out. So there was 2 levels on every factor. And so I put down a 2. That's always the base number, is the number of levels. Then the number of factors, I had 2. So I had 2 levels, 2 factors on my airplane. And if you do that, 2 to the second power is 4. Okay, 4. What does that mean? That means I have to have 4 runs. There's 4 combinations on factor and level settings. And there was. This was a full factorial design, the one we did back here. How do I know that? Because it said there would be 4 runs if I have 2 variables, wing condition and nose condition, and 2 levels for every variable. Nose folded out, nose folded in. Wing condition. Nose folded out, nose folded in. 2 levels, 2 variables there. And so 2 to the second power is 4. Number of runs is 4. Yes, it is. Oh, it must be a full factorial. That's right, because you ran every possible combination. So that's a full factorial. And here's an example. And, well, let's look at this example first. 2 levels, 3 variables. So what if I would have said, okay, nose folded, wing condition, nose condition, and I'm going to have a paper clip. Paper clip on, paper clip off. That's the 3rd variable. And it's 2 levels also. So 2 to the 3rd. How many runs would I have to have if I added that 3rd variable? 8 runs. 2 to the 3rd power is 8. Okay, what if I had 4? I can't think what I'd do with the 4th variable here. But if you had 2 to the 4th, it's now 32. Okay, and if you add 5, it's 64. What happens is every time you add another variable, you double the number of runs. And so it gets rather expensive real quick when you run full factorial designs. Let's go to the next slide and look at this. So there's my 2 levels, 2 factors. Students get mixed up with this, and I'm going to test you to see if I can confuse you. Don't let me. What if I would have said it has 3 levels and 2 factors? Oh, 3 levels. Okay, the base number is level. Oh, that would be a 3 then. That's right. And how many factors? 2. Oh, 3 to the second power, that's 9 if you have 3 levels and 2 factors. So be careful. People are used to using just 2 levels, and in the real world, usually you do on design of experiments, it's usually 2. I've never run one that doesn't have just 2, because the math gets more complex when you do that. So I usually run 2 levels, and but sometimes on the test I switch things on you just to see if you're paying attention to me. So be aware of that. So 2 levels, 2 factors, 4 runs for a full factorial design. 2 levels, 3 factors, 8 runs. 2 levels, 4 factors, 16. 2 levels, 5 factors, 32. Again, what happens is we increase a variable, it doubles the number of runs. And this is not including the replicates. So if you did 5 replicates on every run, which I'd recommend something like that, then this would be 20 runs, 40 runs, etc. So you have to keep that. I'll use that on the test also. I'll say, okay, it's a 2 to the 4th and 5 replicates. Okay, you'll go over here. Okay, 2 to the 4th, 16. Got it. You'll pick 6. No, I said 5 replicates. So you have to take 16 times 5, which if I did it correctly is 80. That's the correct answer. So I'm helping you here on those tricky questions. I hope you're paying attention. All right, and but anyway, imagine running one of these 7 factors, 2 levels, 128 runs, and you ran 5 replicates. Whoa, that's expensive. Okay, so you'd want to be careful there. Now, there's advantages of replicates because you'll find out later. I'm not going to go over it in great detail here, but eventually I'm going to teach you how to determine if those coefficients or those effects are statistically significant. Because remember how we did the effects? It was average when it was positive, average minus the average when it was negative. That was the effect. So what is an effect? It's a numerical difference. And you don't know if that numerical difference is statistically significant. So what I'm going to teach you later is how to do a t-test on those. And if it says, oh, this is statistically significant, there is a difference between the positive and negative settings, then that's how you determine if a coefficient is statistically significant. If a coefficient is not statistically significant, you should not use it in your equation. Throw it out. You should not be using coefficients that are statistically insignificant. So remember what I told you earlier. Just because you have a numerical difference does not mean it's statistically significant. Well, what's that coefficient? A difference between the averages. Well, just because there's a difference doesn't mean it's statistically significant. So we'll teach you that later. But when you do replicates, it gives you more data so you can leverage the central limit theorem. And you can determine better if there's if you have enough evidence to reject the null hypothesis. So we'll go over that later. This is another graph they use in experimental design, a graphical representation of factor effects. So here's A when it's positive, A when it's negative, B when it's positive, and you can do them in priority and say, okay, A variable had the biggest impact, as you can see here, it has the longest line. B had the second biggest, C had the third biggest or the least impact. And it just gives a good graphical portrayal there, and it puts things in priority order. So you'll see that quite often also. This is for the interaction. Interactions are a little bit different, and what you'll end up with is 2 lines. If the lines cross, they say, oh, that's a significant interaction. If they run parallel to one another, no interaction. And so be aware of that, especially if you're taking an ASQ exam. They'll put lines like this and say, what does this mean? Oh, it means there's an interaction between yield and supplier. That's what it means. And we'll show you how to do that plot later. It's a little more difficult. All right, we've already discussed this, fractional factorial design. I can't afford to run a full factorial design, so I'm going to run a half fractional factorial. What does that mean? You throw half the runs out. An experimental design in which some possible combination of factors are not included in the experiment. And we'll describe later what it means by this, but some effects are confounded. Whenever you throw runs away, you could have problems with confounding. I'm going to save that for another module, but we're going to define that later. All right, let's look at an example. 4 factors, 2 level is 2 to the 4th, which means 16 runs for a full factorial design. A half fractional factorial design will take half of those 16 runs and throw them in the garbage, and you run the experiment using just 8 runs. That's a half fractional factorial. Okay? Okay, if an experiment is designed in such a way that 2 effects, main or interaction, cannot be estimated independently of each other, then the 2 effects are said to be confounded. Well, that's going to confound you right now, but give me a couple modules. It won't be in the next one, but 2 modules away, I'm going to define this and in such a way that you'll understand it. So don't worry, you'll get there on that one. This is the matrix for designing experiments. So here is a 2-factor, these x's are factors, 2 factors, and how many runs will be for a full factorial? 2 factors, 2 levels. How do I know there's 2 levels? Because look at this column. There's only a plus minus, nothing else. So there's only a minus or a plus. There's 2 levels. And I know there's 4 runs, so I just come over here at 4 runs. K means the number of variables. I don't know why they call it K, but they do. So the number of variables is 2. 2 factors, 2 levels. Then this is your experiment. You just draw a square out there. That's your experiment. And that's how I got that experimental design over here. I just came to that table and I chopped off a block, and I'm going to have to go back a ways here. There it is. And that's where I got those plus and minus signs. Now let's look at that table again, look for some patterns, because you should never have to use this table to design an experiment, because there's a pattern here. Notice this x1 column. It's always what? Minus, plus, minus, plus, minus, plus, all the way down here to infinity if you want to. Then we say, okay, how many minus signs did this first column start out with? Oh, it started out with 1. Okay, the next one I'm going to double the number of minus signs. Oh, you mean 2? Yes, I mean 2 minus signs. And I'm going to follow it up with what? I always follow it up with the same plus signs. So I have 2 negatives, I have 2 positives. 2 negatives, 2 positives, 2 negatives, 2 positives, 2 negatives, 2 positives. And it follows that pattern down to infinity. All right, now this had how many? 2 negatives. Okay, my next one I'm going to put 4 negatives. Okay, then what am I going to follow that up with? 4 positives, 4 negatives, 4 positives, 4 negatives, 4 positives, 4 negatives, 4 positives, blah, blah, blah. Okay, now if that has 4, what's my next one going to have? 8 negatives. Oh, 8 negatives, what am I going to follow that up with? 8 positives. Okay, 8 negatives, 8 positives, 8 negatives, 8 positives. What will the next one have? 16. What will the next one have? 32. What will the next one have? 64. What would the next one have if I added 128 negatives and 128 positives? And that's that's the pattern. So once I know the number of variables and levels, I can calculate the number of runs. Oh, there's 8 runs. Okay. Minus, plus, minus, plus, minus, plus, minus, minus, plus, plus, minus, minus, plus, plus. 4 minuses, 4 positives. And that will fill up my experiment. Then when I run the experiment, I'll say, okay, run number 1, variable 1, put it at its negative setting. Variable 2, put it at its negative setting. Variable 3, put it at its negative settings. Okay, that's 3 variables. Throw it. You throw it. Okay, write down the response value. Okay, I wrote down the response value. Okay, let's run our second run. Put the first variable at positive, second one negative, all the other ones negative. Okay, throw it, write down your response. Okay, that's how you run an experiment. That's how you design it, that's how you run it. Then of course here I may do replicates of 5 or 4 or whatever the case may be, and I'm going to run each one of those runs 4 times, but I'm going to run them in random order. Why do I run replicates in random order? So I can screen out noise. Extremely important. And there I go. Notice I keep going. So this is for 5 factors, is right here. And then if I want 6 factors, I have to have another page of those plus and minuses. And then 7, of course, 6 is 64 runs. 7 is going to be 128. So now I have 3 pages of plus minus signs, and that's without the replicates. So you can imagine how much that's going to cost you. Wow. Most organizations will not run full factorials, more than 3 variables, 2 settings. 2 to the third is 8. So 8 runs with replicates of 5 runs 40 runs. That's quite a few runs. And it's going to be a little bit expensive. But usually after that, they start running fractional and screening designs. It just gets too expensive. And here I went over the mathematical modeling. Remember, I already did that. The y-intercept was the grand average of all the output or the response variables. Then effect divided by 2 for my coefficient times my x, etc. So hopefully you feel comfortable with that. If you're not fully comfortable with it, you're still all right. We're going to cover it in greater detail in the next module. All right, wow. That was, that one probably challenged you a little bit. That may have challenged you a little bit. You may have to go back and read it, especially how to calculate effects and how to create the mathematical equation. This is the time to listen to it more than once and make that down solid. If you can get that down solid and your vocabulary down solid, the rest is going to be pretty easy. So you could say this is one of the more difficult elements of design of experiments, this module. All right. Remember, you still need to complete that module exam. If you have any questions, please contact me and I'll get back with you as soon as I can. Congratulations, you have completed this module. I hope you have learned something new that will enhance your career. Thank you, and goodbye.